the title might be a little bit out of topic sometimes. So I'm not really in a data center guy. I develop objects which could be a piece and the source of entangled photons and quantum light for a quantum computer. So it's actually on the low TRL side of things, working at the Tyndall National Institute, which is the biggest ICT center in Ireland. There's a colleague of mine, Peter O'Brien, which is talking in parallel to me in a different session on packaging, and we do ICT and other things. But anyway, so this is the motto of Tyndall, which is part of University College Cork, but is an independent financial institution. It's from Atom to Systems. So we have, I had to get used to using this, sorry. So we have everything here from compound semiconductors. I'm actually one of the sources of those, and obviously there's all sort of things, but including quantum, and I have a big project on that. And it comes out of the fact that we do 3-5 materials, and 3-5 materials are the ones on which you can make quantum dots. So this is why we started working on quantum dots, and you will see the quantum dots are here. You see they look like little pyramids. There's a single dot in there. We can put also 2 if we want. Control, so it's a very, very specific and unique system. We're the only one in the world at the moment doing it, but it has potential and it's interesting. So this is what we're working on. And for the rest, we have a lot of classical projects on 3-5 materials. One thing I would like to stress a little bit on quantum is that there's always the high-level talk. Then there is the low-level talk, which is, it's a mystery. Why does it work? Okay? It isn't. Actually, for a community here, which, okay, works with data centers, so does a lot of electronic, but also talks about sending signals from one to the other with light and lasers, it comes out they should be very much the same thing. If you look at Schrödinger equation, they're not very different from Maxwell equation. Okay, one is second order in time, and the other one isn't. But the point is, your solution is a field. Your solution is an object which is distribution, and if it's a field, it doesn't have the same, it has made of things. So it is obviously in different places, but it also have components of the field which are faster than others, hotter than others. In technical terms, have high K components and low K components. So Heisenberg uncertainty principle is the same reason why your laser pulse is broad and has different frequencies in it, okay? It's the same identical reason. And so you can actually say, and I always tell my students, just to shock them a little bit, yeah, you can take a photon, a single particle of light, and set it half left and set it half right. No problem. Okay? And we do it, and we change half of the photon only at the time. We can do that because this is true for a photon, and it's true for an electron, and it's true for any quantum particle. Okay, so I don't have all the time to do all the full typical things I say, but I wanted to at least get something in your brain for questions afterwards. So we need quantum dots, and quantum dot, Google says, a great thing for quantum information processing and realizing qubits, which is what we wanted to do. And we need cryogenics, as was discussed before in the previous talk. So we 10 Kelvin or 5 Kelvin. We don't really need a lot less than that. There are systems in the quantum world which are worse than that, 10 millikelvin or 100 millikelvin, which is more difficult. And quantum dots are single artificial atoms, are single objects made with semiconductors, but they have discrete energy levels. So you can think them as an atom, and it's a very good idea of what happens. And there are atomic-like in their behavior in many ways. I mean, they're a bit more complex than an atom in a way, but they do have, and they have to have some specific characteristics. They have to be uniform. They possibly all identical, which is a very difficult job. We can make them very close to be, but they're not all identical, asymmetries for some things. It's good to know where they are, because if you want to couple a dot to a waveguide, that becomes much easier, and so on. Electrical injection is possible. And I will tell you immediately, our dots don't tick all those boxes. We're working to tick as many as we can, but no quantum dot system out there at the moment ticks all the boxes. Okay, how do we do them? Very unique thing. We take a piece of gallium arsenide, 1111 oriented, means it's oriented. I mean, the gallium arsenide is like silicon, has a cubic crystal, and you just take the direction along the diagonal of the cube. It's just envision, instead of cutting a flat of the cube, just the diagonal. And okay, you get 1, and then you get 3 when you do the wet etching, which is here. You dig a hole here by making normal lithography, maybe a round thing, and then you put a wet etching. And what you get is a 3 triangle a pyramid, an inverted pyramid. They're called pyramidal quantum dots for a reason. And that has 3 crystallographic facets. They are 3 111A crystallographic facets, so they're well-defined crystalline facets. And then we grow a quantum well. We grow like we deposit like we would do by metal organic vapor phase epitaxy, like you would grow a quantum well in a laser. The same thing, identical. The only difference that because of the geometry, we end up, when we deposit atoms which are fast diffusing, like gallium and indium, they get into the middle of the hole. So we don't have a uniform deposition. We have a lot more in the center. When we said a lot more in the center, I mean over 20 nanometers, not over 5 microns, okay? And that's our quantum dot, actually. We can put 1 or many. And then we tend to not extract a lot of light if we do that, because it's an atom. It emits in all directions. How do you get the light you want? So you can do processing, so to, for example, get a little bit of lensing so that you collect more light in the direction you want, or do cavities and more sophisticated ones. This is one example. You can actually take them all out and put them somewhere else. And they are site control, meaning we know where they are, on chip or off chip, on the PDMS. The other thing which they have, which is quite practical, this thing of the atoms which the gallium atoms or the indium atom which run fast in the hole and go in the center, happens also if you grow aluminum gallium arsenide, the barrier, for example. And what actually happens is that you end up having the gallium in aluminum gallium atom, which likes to go in the center. So you have a nanowire in the center. You have a tube, a two-dimensional tube, if you want, three-dimensional in size, but two-dimensional in the electronic properties. In the middle, again, 20 nanometer broad, which is a wire. You can use that to inject selectively your electron in your holes into your quantum dot through the wire, which runs vertically in the system. So you don't have to do any processing to make the wire. It's already there. Okay? And so that was good enough a few years ago to show that selective carrier injection in a quantum dot can emit entangled photon emission by a simple process, which I will discuss didactically in a second. And it was good at the time, 2016, to get a Nature Photonics cover. And you can see we can turn them all on. And most of them emitted entangled photons. Don't look at the start. The turn-on voltage is a bit too high, but it did the job anyway. Okay, and it's actually the only violation of Bell inequality in Ireland. So for the moment, we are the only ones who, so the Bell inequality violation got the Nobel Prize 2 years ago, for those who follow. We didn't get the Nobel Prize, unfortunately, but nevertheless, we can violate Bell inequalities, okay? So they're good enough. That's basically what it says. I would like also to go deep into this mystery of quantum dot. Why do we get entangled photons? And this is really an atomic-like picture. So you have an atom, you have one electronic level. What we call holes in semiconductors is just an empty level. So it doesn't really matter. Okay, so you have 2 electrons, and you just put, exactly like textbook physics, first thing you do in quantum is that. Basically, you put 1 electron spin up and 1 electron spin down. Actually, they don't do that. There is half in this configuration and half in this configuration. Because the spin isn't actually well defined in the electron. If you take a line, you will see that there is 50% chances that the spin is up, which means that you have both of them. So your electron comes with your both spin in all directions and in a specific direction. And the other, when there's another electron coming in, well, it matches the other half spin because it has to do that because of Pauli exclusion principle. They are fermions, they don't like each other. Okay, so spin up, spin down, spin up, spin down. And when you get one of these to recombine, look. And by the way, the energy level changes a bit after that happens, but it's half light polarized spin up and half light polarized if it were spin down. Circular polarized, very easy. And then after a few nanoseconds, you recombine the second one, and it's also half-half. And it's the complementary half. It's the other half. So what you have is 2 photons, which are a mixture of 2 things, but they have a rule between each other. And that's called entanglement. Entanglement is you're not independent, you had some interaction, and because you had some interaction, now there is a rule which links your properties. End of it. That's the definition. You're not a separable state. You're not two different, independent, who don't care about each other things. Okay, so this is how we do that. And we can do a lot more complicated things, but I won't go too much in detail. But what we can do, you can actually see we can stack them. And we can put them one on top of each other. This is big dots, just to show you, because we want to show the image. We normally are a bit smaller than that. But we can make them actually identical or different as we like. And this is a very unique property. You can't stack quantum dots on top of each other and control what happens in other quantum dot systems. And this is an example of molecular state, where we actually put them close enough that it's like two hydrogen atoms together. They form a molecule, right? There's a moment where your two electrons do this. The same. Okay, and you can show this why, but this happens. So we can control that in a systematic way. And this is important for something which is called cluster state emission, hyperentangled emission. The basic idea is very simple. You have a spin here, you populate your state, you emit. The spin stays here, you populate, you emit. And if this stays here, the system has the rule I'm matching this spin. And the rule I'm matching spin is in every emission. So they are all entangled to each other. So you can, in principle, emit millions of them. Now, there's a problem of decoherence, so the spin doesn't stay there where you want. But that said, that is the idea. For doing a cluster state, which has a specific mathematical expression, you need a slightly more complicated design. But we can do that. We can control dot 1, dot 2, have a common state here, and things of this type, which would allow to emit two-dimensional entangled form. We haven't done it yet, but we need to prove that we can arrive to that control. It's a bit complicated to understand what states, because it's not really like an atom. It's a bit more complicated. But anyway, and we also have to fight a nuclear spin. So this is, if you don't do any control of the nuclear spin, you decohere in. This is the scale, 6 nanoseconds. This is up and down. Don't worry, don't ask me what this up and down is, pump and probe and things where it is. It should go up and down. It should stay up, and it decays in 6 nanoseconds. So we need a little bit more than 6 nanoseconds to do a big quantum computer. So we need to learn to do that, even if we can couple the molecular states as I wish. I completely lost control of what time is, so let me know where we are. But we can couple the dots in different ways. So this is one of the things we do. So this is a cryostat. This is cold here at 10 Kelvin, and then you can put a mounting of a photonic chip. This is silicon nitride waveguide. This is a cross section. You can see the waveguides here. Which I don't remember if my postdoc were very clever and they sent some light through them, or just because of the reflection. And then, well, our dots are in well-defined position. So to couple them, many of them, to those waveguides, you just seem to pattern them in a line, put the chip on top, and that's it. Okay? We don't couple 100% of the light. There's a lot more to do to couple all the light in. But this is what it does. And so we've done this, and we show this. And this, for example, is a on-chip experiment. This is a second-order correlation. It means that you excite through the chip your dot. The light of the dot emitter gets into the chip. There's a beam splitter there. Things go left to right, and then you detect if you have a G2, which is small. This was the very first experiment where now we have better data, but I wanted to show the very first. It shows that you can actually do this on chip. Or because you're site control, you can do something slightly different. You can make a waveguide on your system. Now, in this case, the system was a conventional sample where you see this dark here. These are pyramidal dots in an optical microscope. And then they had to do the waveguide turning because they only wanted one dot in the waveguide. 2 minutes on, I have finished. Okay, so the turning isn't because we wanted to show off that we can turn it, but because if we want to take one dot in a uniform field, it wasn't designed for the experiment, you have to. This is a polymer waveguide, and you can see that the light goes through and emits with no big deal. And there's a small change in position of the peak because of the strain when the SU8, which is what it was, it's a polymer transparent resist, cools down and shrinks a bit, and there's a little bit of strain on the quantum dots. But there's similar things that you can do. Now, I was told I need to put a call to action. So I put the call to action, which is, if you're interested, work with us to try to solve this problem, because we need to make a quantum computer, and there's a lot of problems to solve. I will not do the full quantum computer, but I can do good sources, and I can help on many fronts. Okay, thank you very much. I hope I'm on time.
Okay. We do have time for one question. We have time for one question. Yeah.
Scared too many people.
Thank you for the presentation. As of today, maybe I didn't get to this point. How many quantum dots did you entangle?
You don't entangle the dots. You produce light from a dot which is entangled.
Yeah, and your expectation for the future with this technology?
Well, okay, so if we can emit a cluster state, you would need to obtain, let's say, if PsiQuantum wants a million computer with a million qubits, you need at least 1 million photons emitted. Now, at 1 gigahertz, it's what you need to be coherent for. 1 second.
Thank you very much.